Hi, I'm Gary, and I want to show you how I use Cloudy. Okay, this is a picture of 30 Doradus, the nearest starburst, the brightest starburst in the local group. So what we see here is an intense starburst cluster of stars in the very center, and it's a combined radiation from the starburst that is creating the ionization that we see glowing with a dull orange around it. This is probably what's happening at redshift 10, but we just can't resolve it out there. So let's think about this. It looks hopeless at first sight. The orange looks like a tarantula. How are we going to figure this out? Well, it helps to look at it from the right perspective, which Lisa Townsley did when she combined infrared imaging with X-ray imaging of Turdieratus. What you find is what appear to be bubbles in the optical or infrared hollow cavities are actually bubbles of very, very hot X-ray emitting gas at 3 million degrees Kelvin, something like that. So that's what's shown in blue here. And so the scenario is that there's a star cluster. Early type stars are all early type stars are very windy. These winds get thermalized, creating shocks and creating million degree gas. And the million degree gas then combines with the cold gas to form one unified structure. If you look at the numbers carefully, you can't do it very carefully, but within a factor of two or so, the pressure in the hot blue bubbles is equal to the pressures in the orange cooler gas. So you can see this as something like a quasi-static equilibrium with a hot phase in balance with a cold phase. That leads to a very simplified geometry that's going to apply in many circumstances. We have a star cluster near a molecular cloud. The molecular cloud is much, much more massive than a star cluster. So it's a very, very large reservoir of material that can be used to make stars or other things. When stars form from a molecular cloud, those stars are short-lived and they don't move fast enough to get very far away from the molecular cloud that birthed it. And so the stars will be near the molecular cloud, and then the radiation from the stars interact with the molecular cloud, creating successive ionized layers. So here we have the star cluster in the center. It's very, very windy, shocks from the winds. The winds are thermalized, creating this very large hot bubble. So this can have a temperature of millions of degrees and is mechanically heated. Then here's our molecular cloud, which is being subjected to the radiation from this star cluster. So here's it's a cool molecular hydrogen region. Molecular clouds have temperatures of order 100 Kelvin. Hydrogen's molecular, so be thinking about gas pressures here. Different amounts of stellar light penetrate into the surface of the molecular cloud. The H plus layer, the H2 region, so-called, receives the full radiation field from the star. The PDR here in light orange gets a filtered radiation that's not nearly as intense, and then the radiation pretty much doesn't make it into the molecular cloud. Here's the PDR. PDRs have temperatures of about 1,000 Kelvin, and they're atomic. So as you go from the molecular cloud to the PDR, the particle density goes up by a factor of two. One molecule becomes two atoms. The temperature goes up by 10, so the pressure goes up by 20. And then here's the H plus layer. The pressure goes up by another factor of 20 because one hydrogen atom becomes an electron and a proton. The temperature goes from 1,000 to 10,000 Kelvin. So the gas pressure goes up by a factor of 400, causing a photoablative layer of gas that moves away from the molecular cloud. If you look at the dynamics, ionized flows go through various phases, and the equilibrium phase that is quickly reached is a D critical ionization front. This geometry is very commonly observed. This is a planetary nebula, the opposite end. This is the death of a low mass star. Then this is Yohua Chu's image. She took HST imaging on the left, so you can see what will become a white dwarf. It's the nucleus of a planetary nebula. And then you see this very chaotic structure around it that looks slightly hopeless. How will you understand that? Combine that with X-ray imaging, and you see that the hollows are filled with hot X-ray emitting gas produced by these stellar winds. So this is a very common geometry. So we have very hot, very highly ionized gas, atomic gas, and molecular gas. Cloudy's always been designed to go to the same limits that nature does. And so this plot is from the Cloudy 2013 release. The horizontal axis shows a huge range and intensity of the radiation field. The radiation field is a million degree black body. This is parameterized here by the energy density temperature. So this would be a very weak radiation field, something like the intergalactic medium, whereas up here we have very, very strong radiation field, like the interior of a star or the universe before recombination. Now this scale is a huge range of densities going to below the intergalactic medium up to approaching stellar atmosphere densities. And there are simple thermodynamic limits that you should go to, local thermodynamic equilibrium and strict thermodynamic equilibrium, and then an ionization limit in the case of Compton exchange. So cloudy behaves in all these proper limits. The colors here indicate the ionization of hydrogen, with blue indicating fully ionized hydrogen and red indicating molecular hydrogen. So the hydrogen ionization goes through huge ranges across this plot. The yellow bubbles indicate some commonly observed astronomical sources. The approach here is that if we take care of the microphysics, Cloudy's a microphysics code, the macrophysics will take care of itself by combining and building up a geometry from the microphysics. This is two views of a similar geometry. On the left is the Orion Nebula, the famous Bob Odell imaged with HST. And on the right is the homework problem we're going to start working on, and that's the fingers of creation, again, seen with HST. And so what we're looking at is the same thing. We're looking at a thin layer of ionized gas on the surface of a much, much larger molecular cloud. In the case of M16, we can see this in cross section. So we can see there's a very dark silhouetted molecular cloud. There's starlight striking the surface of the molecular cloud from stars that are not in this field of view. That creates this ionized layer. Then this gas pressure, this overpressuring caused by going from molecular and cold to ionized and hot, causes the gas to stream away in a quasi decriticalization front approach. So you can see these streamlines of gas material. On the left, we're looking at the Orion Nebula, where we're actually looking at this geometry face on. So we're looking at basically what we're looking at is a flat pancake that's pointed towards the Earth. So with this perspective, we're going to go on and start thinking about doing a model of the M16 H2 region.